Hi, welcome to another presentation on generative artificial intelligence. This presentation is going to dive in and talk a little bit about large language model memory. This will be a pretty short presentation, but we'll dive into, some fairly technical details. So there's a number of challenges when dealing with extended conversations with large language models. The first thing to keep in mind is that large language models have a limited context window. Now, we'll talk about this in more detail in a few slides, but basically, you need to keep all the details of your conversation within this context window. And so that becomes a pretty big issue in terms of dealing with long-term memory. Really, if you think about it, a large language model only has a short-term memory. The next issue to think about is that the attention approach that large language models are primarily following these days is a probabilistic algorithm. And so information that's older may have a lower attention score as your conversation gets longer, and therefore that information may not come up in the probability matrix. The next thing to keep in mind is that LLMs aren't actually storing information. They don't have a persistence internal state. A large language model is not a database. Instead, it's continuously producing, the conversation with every turn in the conversation. And the final thing is that there can be some information diffusion or degradation as time passes. Details from earlier parts of the long context can become less distinct. So let's talk a little bit more about how LLMs actually work. So LLMs process tokens as units of text. And so that's why we talk about things like tokenization and so on. Tokens are not always whole words. They can be a part of a word, but they're meant to be a part of a word that has meaning. And tokens matter for LLMs because our context windows are basically defined in terms of how many tokens they can handle, 4,000, 8,000, 100,000, whatever. And the more tokens you use, the greater the cost and the greater the impact on the speed and so forth. And different LLM memory strategies will manage tokens in different ways. Um, so let's talk about some of these other strategies in a moment, but first let's talk a little bit more about context length. So context length is a critical factor in LLM performance and capabilities, as we just saw when talking about tokenization. Um, Different LLMs have a wide range of maximum context lengths. So, for example, GPT-4 somewhere between 8,000 and 32,000. Claude 2 is around 100,000. Llama 2 is around 4,000, and so on. And when you go outside the context length, well, obviously, then you've hit your maximum and you typically will start a new conversation. And so managing a context is crucial for effectively interacting with an LLM. All right, so by default, the simplest model for handling memory in LM is sequential memory, where when we're having a conversation with multiple um, text inputs strung together, we essentially append the new input to the existing context until we hit the maximum. This tends to be effective for short to medium conversations, but when you have a lot of information, obviously you'll overrun the context length, and that causes problems. The next approach is what we'll call the sliding windows memory. The basic idea is that we're gonna just keep track of the last X amount of memory. And if we hit the max, we'll just drop off the stuff that was oldest. So this allows for the conversation to keep going, but the older the input was, the old inputs will drop out. So this can have problems with long-range dependencies unless you somehow get the more recent information to pop up. So for example, if in my initial prompt I mention, Christmas of 1945, but then I go beyond the context window while still continuing to converse, the LLM will have forgotten that Christmas of 1945 date, for example, because we now are beyond the context window, and so all the original stuff has dropped out. So if you want to work in an LLM that has sliding windows, if there's important information, you're going to need to refresh that information during the conversation from time to time. Another approach, which is kind of similar to the refreshing approach I just mentioned for dealing with the windows, is a summary-based method for memory. This is where we know that we want the conversation to go beyond a length limit, and we're periodically going to generate a concise summary of the conversation that will replace a portion of the detailed history and memory. And then those new interactions are appended to the summary until we hit our next summarization point, and then we can generate a new high-level summary and so on. So again, this is has some advantages over some of the previous approaches, but it also has some drawbacks as well. Finally, one of the most popular approaches lately is what's known as retrieval-based memory or retrieval augmented generation. The basic idea is we're going to extend our LLM with a vector database, and the vector database is going to store some information. Now, the information that's stored in the vector database could be the conversation history that we've been doing with the LM. It could also be external documents, it could be other things. And the basic idea is for each new interaction, when we're generating a response, the LLM is going to use a semantic similarity search to pull out relevant information from the vector database to help build its response that it's going to send back to the user. So essentially adding a long-term memory to our LLM, which doesn't really have a long-term memory. So thanks for watching this video.